So continuing on with 3.5, we're going to fill in the last three proofs now. So page 4, if M is the midpoint of Ln, then MP is equal to Lm plus NP. And we know what all those segments are by just looking at our picture right here. So they've given us the segments, we need to give them the reasons. So our first statement is going to be our hypothesis, or our given statement, the stuff that is in between the if and the comma if we're given a conditional statement. So our first statement is just going to be that M right here is the midpoint of Ln. So this little piece right here, and that's given to us. Okay, so now knowing this fact that M is the midpoint of Ln, we have to ask ourselves, well, what does a midpoint create? And a midpoint creates two segments that are going to be equal to one another. So if M is the midpoint of Ln, then up here we can say that these two segments that are created, Lm and Mn, that they're equal to one another. Okay, and that's going to be our second statement, that Lm equals Mn. And we have this statement by using the definition of a midpoint. Okay, so we keep on going. Mn plus Np is equal to Mp. Okay, so far we haven't seen Np or Mp pop up, so we have to ask ourselves, how in the world did they get those to pop up? So if we look up here at our picture, okay, so we have Mn right here, this little piece, and the second part says plus Np, and it's equal to Mp. So we've got little piece plus little piece is equal to big piece. Well, that sounds an awful lot like the segment addition postulate. So that's how they got this third statement, was by using the segment addition postulate. Okay, next up, statement 4. Lm plus Np is equal to Mp. So if we look between statements 3 and 4, the only thing that we see change is right there. Mn became Lm. And if we look back at our statement 2, we found out that Lm and Mn are equal to one another. So we can switch them out at any point. So that's exactly what they did right here. They took Mn and they swapped it out for Lm by using the substitution property. Okay, and then lastly, from our statement, we saw that we wanted to have at the end, Mp is equal to Lm plus Np. And currently we have Lm plus Np is equal to Mp. So we need to switch the order around. So we're able to easily do that, put the Mp on this side and the Lm plus Np on this side by using the symmetric property. Okay, let's look at page 5. Okay, and the good thing about these proofs is that a lot of them will start to follow the same pattern. So once we get a couple of them under our belt, we can go through them a lot quicker. So page 5, given that CE is congruent to FE and ED is congruent to EG, we need to prove that CD is congruent to FG. So they give us all the statements except the first one. So we need to fill in that first statement and our reasons. So we always know what our first statement is going to be. It's either going to be all the stuff following the word given, as in this example, or in previous examples, we've seen conditional statements where it has if something, comma, then something. So our first statement is going to be everything between the if and the comma, basically. So our first statement will be that CE is congruent to FE and ED is congruent to EG. That is given to us. Okay. Next up, they gave us this statement: CE plus ED equals CD, FE plus EG equals FG. So we look over here in our picture. We have CE plus ED is equal to CD. We have FE plus EG is equal to FG. Okay, so we were able to use the segment addition postulate to find out both these. Segment addition postulate telling me that one big segment cut into two, add the two pieces together, they equal the whole. So let's keep going. Next up, we have FE plus EG is equal to CD. Okay, so it looks kind of similar to this statement right here. Okay, so it seems like they used some kind of substitution. At first, we're going to think maybe they did FG for CD, but that doesn't make any sense. But what does make sense is they said up here that CE is congruent to FE and ED is congruent to EG. So basically, we've got these two right here are congruent, and these two right here are congruent. So if these are congruent, we can switch them out at any point. So all they did is they took the first part of statement 2 and they rewrote it right here by subbing in the two pieces on the left side. So that's how we got FE plus EG is equal to CD using substitution property. Okay, next we have FG is congruent to CD. Okay, so they had this and turned it into this. How did they do it? Well, they took the second part of statement 2, FE plus EG is equal to FG. And so anywhere that we see FE plus EG, we can substitute it with FG. So again, they just use substitution property here as well. And then lastly, we wanted to prove that CD was congruent to FG. And currently we have FG is congruent to CD. So we basically already have it, but they want it in a right order. So we're going to switch the order by using our symmetric property. All right, lastly, let's do page 6. So we are asked to prove that if M is the midpoint of Ln, then Ln is equal to 2 times Lm. So we start with our first statement. So this time they kind of combine the prove and then the if-then statement. So our first statement is still going to be everything between if and the comma. So M is the midpoint of segment Ln, and that is given to us. Okay, so next, they give us that Lm is equal to Mn. Okay, so we ask ourselves how in the world can they know that? Well, if M is the midpoint of this segment Ln, then that means that these two pieces are halves of the whole thing, or they're equal to one another. So I can say that Lm is equal to Mn by the definition of a midpoint. Okay, next up, statement 3. Ln is equal to Lm plus Mn. Well, I haven't really seen Ln at this point except knowing that it's the whole picture. So if I look at my whole picture, Ln is equal to Lm plus Mn. Well, that looks like the segment addition postulate to me. They're telling me the whole segment is equal to this piece plus this piece added together. So this is going to be using the segment addition postulate. Okay, next up, Ln is equal to Lm plus Lm. Well, the only thing that changed was this Mn became an Lm. Okay, and how did I know I could make that switch? Well, if we look back up here at statement 2, Lm is equal to Mn. We already showed that. We already proved that. So that means that I can make this switch anywhere. So I have my fourth statement by using the substitution property. Okay, and then finally, the thing that I wanted to wind up with at the end was that Ln is equal to 2 times Lm. And currently at this point, I've got Lm plus Lm. Okay, so you might be a little bit boggled on how we're doing that. So let me show you an example. Let's say that if I have x plus x. Okay, so x plus x. And if I want to simplify that, if I want to make that seem a little bit more concise, I could just say that if I have x plus x, then overall, I've got 2 x's. Okay, that just makes sense. If I've got x plus x, that means I've got 2 x's. So that's all they did right here. So we had one Lm plus another Lm. So they just took that and rewrote it. And they said, well, we have 2 Lm, so let's just rewrite it as 2 times 1 Lm. So all they did right here is you might at first think addition property, but in fact, they're actually using the property of combining like terms. Okay, so we talked about the difference between addition property and combining like terms was that addition property would apply if we were adding things to both sides of the equal sign. But in this case, we're just adding two things together that are on the same side of the equal sign. So that's why for this case, it's just going to be combining like terms, not using the addition property.